So today we're going to talk about check valves in the biopharmaceutical industry. We're going to talk about the history and development of check valves. We're going to compare designs between some of the early, what we would term hygienic check valve designs in the newer aseptic designs that we have actually. We'll end this presentation talking about applications in biopharmaceutical, in parenteral processes, both upstream, downstream, and on clean utilities. So with that said, I'll get started. I created this material to answer some common questions that have come up over the years in conversations with customers. Those questions actually led to the development of some of our most innovative products, our aseptic check valves. And so to answer the first question that you see on your screen, are there any check valves that are designed to be used in aseptic pharma process on services like WFI and bioprocess? The answer is yeah. We developed one specifically for that. Second question that we'll answer today, why aren't traditional spring-assisted check valves and ball check valves used in biopharmaceutical or parenteral process applications? What characteristics in check valves are desired for these applications? And then again, finally, we'll talk about the applications for these types of valves. So to start out, we're going to take a look at and talk about early designs, a little history before we start. So check valves originated during Roman times. The earliest check valves were created by the Romans for their aqueduct systems. And over the last 100 years, most of the check valves that you'd be familiar with, the non-return valves, like swing check valves, guided disc piston check valves, ball checks, wafer checks, spring checks, and diaphragm check valves, that technology is about 100 years old. Two from that list, the spring-assisted check valves and the ball check valves, both shown below, were adopted over time from industrial use for use in hygienic applications in the food and beverage industry. And those are the two prominent ones that you'll see in these hygienic food and beverage, health and beauty process applications. And the ball check valve, pretty simple, brilliantly simple design. And it's basically a ball that sits in the waterway. And if flow comes in through the inlet here, you can follow my cursor, it'll push the ball up into this little cavity that you see. The valve is shaped like a piece of Y tubing, but it's that simple. Flow comes in, pushes the ball up that cavity, and flow goes straight forward and straight through the valve. Now, in reverse flow, when there's an upset event that causes the pressure at the outlet of the valve to be higher than the inlet pressure, flow is going to reverse. And if that happens, the flow will push the ball and it'll push it into that inlet waterway where it'll prevent flow. Pretty simple. The other simple and older technology that's been adopted for hygienic service are spring check valves, and they're pretty simple as well. So in this case, you've got flow entering through the inlet here. It contacts a thermoplastic disc that has a spring behind it that's in compression. And when the force of flow, the pressure at the inlet exceeds the spring force that's trying to close this disc, of course, the disc will compress the spring and I'll get flow through, around, and through the springs and guided spring through the outlet. Of course, if flow comes in the other direction, what's going to happen is the spring will elongate, pushing the disc into the inlet and prevent backflow. Pretty simple design. So if you take a look at these designs, they've persisted over the years, and they were adopted early on for the pharma industry for non-parenteral product process applications and also for gas applications. But those applications only. In the biopharmaceutical and parenteral API pharma industry, in other words, for if they're making chemical drugs for injection or for an inhalation, those check valves designs are not suitable for process applications. The biopharmaceutical and parenteral industry uses those for air and gas and for self-sanitizing, sterilizing liquids like buffers, acids, and bases and CIP, but they won't use them on WFI, on drug process, additives, on intermediate drug process or final drug process. Why? Because they're deemed non-acceptable, because they're difficult to fully sanitize, and because of other factors regarding their internal design, namely that They are unable to fully drain. There's an internal integral dead leg. And if you look at the spring-loaded design here, most of the designs have a little cavity here that doesn't fully drain. And on the ball check, you've got this dead leg behind the ball that's tough to clean out. So that's one reason. The second reason is that the spring-assisted check valves in particular have a hard time achieving needed CIP velocity and turbulence across the internal components and cavities. They're tough to clean. In addition, both designs suffer from particle shedding via the thermoplastic ball or the spring-loaded disc contact with the seat. A customer of ours in Ireland several years ago decided to test our design against the spring-loaded check valve that they were using. And what the guy did was he built a little test stand and it took dry nitrogen and he pulsed it through the check valve. So the check valves would open and close, the disc would open and close. And then at the outlet of the check valve, he put a sterile vent filter. And basically, he weighed the sterile vent filter before the test and he weighed it after the test. So he cycled these check valves, ours and a spring-assisted check valve, like the one shown here, over about a month, just pulsing the nitrogen open and close. And at the end of the test, he weighed the vent filter to see what there was a change in the mass. And there was on the spring-loaded disc in particular. There was a huge increase in weight, and the weight they found after evaluating the spring check valve were little bits and pieces that flaked off the disc. And when the disc is forced into the seat, you get particulate generation. Lastly, spring check valves also suffer from spring material choice limitations. If you can use stainless steel, again, on a non-process application, the spring check was fine. But on process applications, in particular, where you've got aggressive buffers or acids or basic material, and you need a high nickel alloy, it's tough to find springs made in high nickel alloys. So that's another disadvantage of those designs and why they aren't used in biopharma or parenteral process applications. So in 2009, we realized that there were some unsolved problems with traditional check valves and why bioprocess engineers were hesitant to use spring-loaded or the ball checks also on process applications because of these limitations on these valves. We started manufacturing our check valve design in 2009, and the design of this valve really overcomes all those limitations. So the disc precisely guides, and I've got the cutaway views of both our Steriflow vertical check valve and the SHC, Steriflow horizontal check valve. And you can see the different components. You've got a disc here sitting on a sloped seat. The same thing on the horizontal. This disc is sitting on a sloped seat underneath here. For the SVC upflow model, with normal flow in the upward direction, when the pressure from the flow exceeds the weight of the disc opens, it travels up through the integral disc guide, which is part of the upper body, and it just slides up. Flow goes around the disc through the holes and downstream. Very simple, elegant operation, no springs. And the same thing occurs on the SHC. Flow comes under the disc. When the pressure under that disc exceeds the weight of the disc, plus any back pressure, of course, the disc guides open, slides up to the top, and you get flow around the disc and through the holes. This design eliminates all crevices, has minuscule cracking pressure, as you can imagine, and enables complete high velocity and turbulent CIP and full contact SIP. There's a very simple design. There's also very little system pressure loss, as you would imagine, with this design, because once that cracking pressure is met, it's minimal. It's inches, basically, it's hundreds of a PSI. Once the cracking pressure is met, the flow causes the disc to rise instantly, and I go to full flow with very little cracking pressure. So those are some of the good things that come about. So this is a little more on how this valve works. So flow comes under the inlet again, and when the pressure exceeds the weight of the disc plus any back pressure, the disc will immediately slide up off the seat and you go to full flow. It slides up in the integral guide here. So flow, it's designed to flow around the disc, but also through these interesting angled holes that surround the perimeter of the disc. So a couple things about that. Cracking pressure, as I mentioned, is minimal. And secondly, full flow is instantaneous. Once I crack, the disc moves to the full flow position. And because of that, because there are no springs or nothing behind that disc, I have very little pressure drop across this valve. It's interesting to note that the holes that surround the perimeter, in most cases, equal, or at minimum, equal the flow area of the inlet and outlet. There's that much flow surface on those discs. So in reverse flow, of course, the disc is pushed down on the seated area that you can see here. And with differential pressure, I can go bubble tight and get a really tight seal. And I actually, without a large differential pressure, I get a tight seal. And you'll see that a little bit later on. I'm going to show you a chart with the pressures required for sealing. The SHC model operates, again, pretty much the same. Flow under the disc lifts, flow goes around the disc down into this drainable. You can see the beginning of this little channel here that's at an angle that ends up coming out here. So flow, once it goes through the holes around the disc, it drains down through this slope chamber to the outlet. In the same way, on the inlet side, it is severely sloped. So in other words, you get no holdup on the horizontal design. Nothing is held up in the valve itself. For reverse flow on the horizontal, same concept as with the SVC, the vertical valve. When the pressure on the outlet side from the force of flow exceeds the pressure on the inlet side, of course, the disc is going to drop on the orifice and seal it. And all pressure is pushing the disc into the seat. Again, there's never any holdup with that valve as well. So we've got 3 disc materials available for the SVC upflow and the SHC horizontal check valve. And they are TFE, Teflon, pure Teflon. We have a 316L disc with an EPDM dovetailed O-ring that's inset into the top of the disc. We also have a solid, by the way, 316 disc as well. And lastly, we have a peak disc for a little bit higher temperature if that's needed. The cracking pressure on the disc, as I mentioned before, very low, 0.04 PSI differential required to crack open the disc, which is 2.76 millibar. And again, once I crack the disc, once the pressure lifts the disc, it immediately slides up to the top of the disc guide and I go full flow instantaneously. The 316 disc weigh a little bit more as you would expect. So the cracking pressure is 0.13 PSI differential, or 8.96 millibar. Again, minuscule compared to any other check valve technology that's out on the market. Interesting thing happened back in 2012. I was at a biopharma plant in Belgium, and the fellow that I was visiting that day had FDA inspectors in the plant. And during my meeting in his office, he told me that the FDA had mandated that they put some kind of backflow prevention in their sinks in their R&D wet lab to prevent drain backup. The FDA said, you know what, you get an overpressure event in the drain line, you're going to have nasty fluids coming up into their research sinks, which were in a classified area. And so they had to do something. And the guy was worried. They could not use a spring check in the drain lines under the sinks, of course, because with a spring check valve, I'm always going to have a dead leg of fluid sitting in that drain above the poppet, because even with a low half PSI cracking pressure, for example, I think is one of the lowest that you can get on spring check valves. That means I'm going to build up at least 8 inches of water column in that drain that will never drain because it's not enough weight to open the poppet on the spring check valve. So he couldn't do that. Then he had looked at using an automated diaphragm valve or ball valves underneath the sink that he could automate with the press of a button. He could close the valves to prevent backflow. But if they were using the sink and letting water or dumping fluids down, of course, they would open that. But that was going to be a huge cost. And so when we visited this, the idea for this check valve of a downflow check valve for aseptic drain applications kind of came to life. And that's where this design came from. So we went back to engineering, and after a month or so came up with an idea, and that is we'll basically take the SVC design, the check valve, turn it upside down, which basically is what you're looking at here on screen. The disc will fall into the guide, the outlet body. It'll slide down and just rest at the top of the guide, but it'll always be open and draining. So in a drain line, this check valve is always going to be draining. Now, the beauty of the innovation here was in our disc material choice. We found a disc material that has a low density polypropylene, and this disc will float on top of water. And I remember we had some disc machined and we just filled a bucket of water. We threw the polypropylene disc in this bucket and they popped up, were very buoyant, riding the top of the water. So that's what we used. We tested it and it worked. And to my knowledge, the only septic design check valve that can be used in drain lines to this day. And really cool, but simple idea that our engineers perfected. And that's what you're looking at right here. And how it works, of course, since the disc sits at the bottom of the lower body cavity by gravity, and of course, force of flow keeps it down as well. So it's constantly open, allowing continuous draining. The only time that disc will close, of course, is when a water-based fluid backs up in the drain, in which case the disc will ride that column of water back up and it will seat here and it'll seat tight. So anyway, that's how it works. Pretty simple. This valve, the SVC downflow, as well as the SVC upflow and SHC, as I mentioned, all of these are CIP and capable. They're very easy to clean and to sanitize and to SIP. So here's the disc that we use. It's a special FDA USP Class 6, very low density polypropylene disc that we use. I mentioned earlier that we talk about the leak rates in reverse flow at differential pressure for the various discs and sizes that we have. I put this chart together from our data sheet. This information is there, but you can see that maximum leakage on any of our designs with a 3 psi back pressure is 1.1 milliliters per minute, and that's on the 2.5 to 4 inch check valve. You can see that here. And just out of interest, this past week, I thought, you know what, I'm going to compare that to ANSI FCI Class 6 leakage criteria that you'd find for control valves, for example. What is considered Class 6, which the industry terms bubble tight leakage. And this is the chart that I downloaded from the ANSI FCI website, and it shows port diameters of various valves. So 1 inch and under valves, they can leak up to 0.15 milliliters per minute and still be considered a Class 6 shutoff. Now, it's interesting that the test for Class 6 shutoff is to put a 50 psi differential across the valve. And I thought it was interesting to note that at a 3 psi back pressure, differential pressure, these are the leak rates of ours, and some of ours exceed the leak rate data at 3 psi back pressure. We know from our testing that all of these valve sizes and all of these discs will seat bubble tight, have Class 6 tight at 30 psi differential pressure. So we actually exceed the ANSI Class 6 ratings, which I thought was interesting. We're going to take a look at some applications quickly here. And these are applications for the SVC and SHC. The first one we're going to look at is on WFI, and specifically on hot WFI. So I've got the illustration of a WFI loop here on screen right now. You can see the SVC or the SHC has been used on a hot WFI point of use after the point of use valve as it feeds heat exchangers for the creation of ambient WFI. So this prevents, in the rare occurrence of a higher pressure event occurring downstream of the point of use, using our check valve here will prevent backflow of WFI back into the loop, which you never want to occur. When I first heard of this application, and another one you'll see in a minute, I thought to myself, how is that ever going to happen? It's a rare occurrence. And so they put check valves here for risk minimization. So even if it's a 1 in 20,000 event possibility, you never want that water that's left the loop to go back into the loop for contamination worries. And that's why they're doing this. On this application, again, the SVC downflow you could use, or the SHC could be used as well. Here's another really interesting one on hot W. Several years ago, a customer approached us, and after learning about our check valve, and he said, can I drill a hole in the check valve disc so that I can allow a backflow of my hot WFI standby pump loop so that I can keep this standby pump at least 80 degrees C so that it truly is standby and ready to go at a moment's notice. What the guy had been doing prior to that was using a diaphragm valve and just cracking that diaphragm valve open, trying to allow a fixed amount of flow back through this pump, and a centrifuge pump and other pumps for that some will allow backflow through the pump. So he would crack this diaphragm valve, let a minuscule amount of flow through here. He had temperature sensors and just made sure that this entire loop was kept at above 80 degrees C. Problem was that with a diaphragm valve, it's really tough to precisely meter a flow that you need. And he gave up on that. And that's when he got the idea of, hey, if I can use your check valve here and put an engineered hole in that disc, I'll know exactly what the amount of backflow through this loop. And because once these pumps start, my differential pressure from the loop to the suction side of the operating pump, it's going to be a fixed differential, and therefore a fee can determine what flow and what size hole to make. So we did that, and it worked like a champ. We had some learning to do when we did this. The first disc that we did this was with was either a PEEK or a Teflon disc, which we found with the standby pump turned on, there was such a surge of force that it crushed the Teflon disc. So lesson learned. So for this application, we always use our stainless disc with or without the EPDM seal. So keep that application in mind. It's a cool way to temperature validate the standby pump. So here's another. This is on ambient WFI at point of use valves. And again, this is fairly common for us to get this application. And you can either put it after the point of use valve, right? Or you can put it after the hot WFI to ambient WFI heat exchanger as shown up here. So either will work. This is more towards the end of the loop. Some people prefer to do it this way, but that works. And we've sold valves on that application. For the SVC downflow check valve, here's that sink application that we discussed earlier with the biopharma plant in Belgium. This is what this application was all about. Again, putting this downflow check valve under a sink, and it works well and prevents the backflow of any fluids up into that sink. This idea, people started applying it and using it on process applications in the biopharma plant. And one of the applications that we know is on a centrifuge outflow on the centrate line. There's usually a bypass line downstream of the instrumentation that's measuring what's in the centrate, and the check valve is in this bypass line. It's bypass typically to drain. And in this event, they put a downflow check valve to prevent the rare occurrence, again, of positive pressure in the drain that exceeds the centrate line pressure. So the check valve would prevent backflow of this waste centrate into the process line. Similarly, on diluted buffer outflow on an ultrafiltration or diafiltration application, where you're putting along with ambient WFI into the ultrafiltrate or diafiltrate vessel, usually you'll have instrumentation and then a bypass valve to drain that will activate if these instruments are reading non-spec buffer. This valve would open and divert that non-spec buffer to drain. Put a check valve here again to prevent the rare occurrence of an overpressure event on the drain or recycle line that might cause that non-spec buffer to back up into the process line here. So that's why that is used. And similarly, on a buffer dilution system, on ILD system, again, same setup. If non-spec buffer comes through, and this happens a lot, by the way, because it takes a while for the pumps, the flow rates to get the spec buffer, what will happen is they'll bypass the diluted buffer to recycle or waste until it meets the required dilution parameters to be used in the chrome column. Similarly, downstream of the chrome column, if the eluate is not what is needed, it'll be bypassed to drain until such time it meets spec, and then this drain valve will close. And here's another check valve in a line to waste that you would put to prevent backflow in that line, especially that line, because we're getting closer to final purified product at that point. This is a photograph I took at an ILD skid manufacturer that makes ILD skids and uses our product. And this one was used on a ILD system on what the customer described to me as an overflow line. And it was interesting that this overflow line dumps into a horizontal sloped drain header that also is where the SIP condensate will drain into. And what gave me a clue to that was this little 1/2-inch tri-clamp fitting here. And I can tell you when this skid is built up, there will be a temperature sensor above here and a steam trap right here. So this header is taking hot condensate from SIP into the header. At the same time, if there were an overpressure or event and I had an overflow, I'd have diluted buffer or overflow, whatever, coming down into here. This check valve is here to prevent that rare occurrence when the pressure inside this drain manifold would raise above the pressure above here, in which case I'd get a backflow of fluid and the SVC downflow would check there. So those are the more common applications that we know about. We don't know about all the applications that this is used at. And for that reason, I'd like to ask you at the end of this, if you have applications where you think you could use this or where you do use these valves, please type a brief sentence in the survey at the end. We'd appreciate hearing from you. I will answer all questions. Last application I want to show you, and then we'll quit, is an application that the customer could not use standard spring-loaded check valves, and he couldn't use our downflow valve either, but it's worth talking about because it's fairly common. So this particular customer, and this was a piece of a drawing that he had sent, they had a drain manifold that was draining SIP condensate into this sloped drain manifold. On that same manifold, they had an AWFI, ambient WFI sampling funnel drain that connected to that horizontal SIP drain manifold. And what was happening is, because this was open to atmosphere, this is an air brake here, this funnel, every time that they would SIP, you'd have flash steam vapors coming out of this SIP funnel into this classified manufacturing space where they wanted to take samples. And so you've got flash steam vapors coming up, which is not good. And folks, I can tell you, having visited plants all over the world, that this is a common occurrence, getting vapors up through a drain. You cannot use a spring-loaded check valve here because I'd have a dead leg. Again, for the reason that we described earlier. Spring-loaded check valves, there's always going to be a dead leg above the disc because of the spring loading. So he couldn't use that. He wanted to use our SVC downflow, and that would work. It would drain, the ambient WFI would drain beautifully through that. However, if vapors were coming up through that drain, that check valve would not close. It needs water because it's the only way it's going to rise. If there's water, that the disc rides up and seals off. So this isn't going to work either. So anyway, I wanted to share that. Those are an application where no check valve is going to work. And I think this fella ended up specifying a ball valve and made an automated close system or a manual system where when they were sampling, they would open the ball valve or diaphragm valve, allowing the AW ambient WFI to drain down. But then all other times they would close that valve to prevent that flash steam from coming up out of that sampling funnel. Anyway, that's all I had today for you.
I don't see any questions in the question box. Some of you may have come in after but there's a little icon with a question mark at the top of the screen. And that's where, if you have a question, you can submit it. We'll wait a minute. We have 5 minutes before our time is over. But if you have something now, or if not, when you leave, when you log off, there'll be a survey will pop up, and the survey will ask for your feedback and also have a space for you to ask questions in there. And Karl will get back to you by Monday. So if you have any now, though, that you'd like to ask in front of everybody, then you can type it in. I don't see any yet.
All right.
Okay.
Diane, I think we can close it down. Again, if you have questions, you can put them on the survey and we'll answer. So everybody have a good weekend, and thank you. Thanks for attending.
Yes, thank you. Have a good day. Bye-bye.